Okay, so what we're going to have a look at for the remainder of the session today is start to look at the first of a few network theorems that we can use to help solve network problems. As a starter to that, we need to consider what constitutes an ideal voltage source and or an ideal current source. If we have a voltage source like this one here, Vs, and that's 10 volts, and we draw by convention a voltage arrow pointing to the positive terminal, so the other end must be negative, we expect the current to flow in that direction, okay, and if that's ideal, we would get 10 volts regardless of how much current we drew from that. So with that we're making an assumption whether we draw 1 amp or 1,000 amps, we're still going to get 10 volts out of the source. That would be what we'd get if that was ideal. And this is the important point that you need to focus on, because three of the techniques involve you knowing that an ideal voltage source would have 0 internal resistance. Any real voltage source cannot achieve that ideal. As you see last week, as you load your signal generator in the stop zone of your filters, your input voltage starts to drop. And if you think about, if you put the lights on in your car and then try and start it, what happens to the lights? They go dim. Okay? So there isn't an ideal voltage source that exists out there. We can try and make one look like it, and we can model what a real voltage source does, and that's what we're going to talk about now. So, ideal voltage source has an internal resistance of 0. So, if we want to represent a real voltage source, let's consider that this circuit is your typical 9-volt battery. We can model that 9-volt battery, or let's say it's a 10-volt battery. We can model that 10-volt battery by saying that's an ideal voltage source of 10 volts. This bit has got 0 ohms about it. Yeah? It's got 0 ohms internal resistance, and we put it in series with its actual internal resistance. So a real voltage source can be represented by an ideal voltage source, Vs, in series with its internal resistance. When the circuit is open voltage, open circuit like it is now, we would measure, if we put a voltmeter across the terminals, we'd measure 10 volts, because there's no current flowing. Okay? So when the circuit is open, the terminal voltage will be Vs. However, when a current is drawn, some of this voltage will be dropped across the internal resistance. So, in order to illustrate that, if the open circuit voltage of a battery is 12 volts, so what we're saying is Vs is 12 volts, and its internal resistance is 0.5 ohms, find the terminal voltage of the battery when currents of 2 amps, 20 amps and 80 amps are drawn from it. Okay, so have a go at that. So our calculations say here at 2 amps. We're calculating the volt drop across the internal resistance as 1 volt, leaving us 11 volts at the terminal. At 20 volts, we drop 10 volts across the internal resistance, leaving us with 2 volts at the terminals. Theoretically, with a current of 80 amps times 0.5, 40 volts would be dropped across the internal resistance, leaving us a terminal voltage of minus 28. That's not possible. So in theory, when VRS, the internal, the voltage across that is equal to 12 volts, terminal voltage equals 0. Put underneath there. This would be when current I was equal to 12 over 0.5 equals 24 amps. So the absolute maximum current that we could draw from this supply would be 24 amps. But without zero terminal volt, you won't get there, Carl. That'll melt everything in most sources before you ever got anywhere near that. That's only a model, remember. The idea is we can model a real voltage source by considering its internal resistance. And you've already come across it in your diagrams for your attenuators, remember? When we've done that on multisim, we had to say we're going to put our actual source at twice the voltage we wanted because you're losing half of it across the 600 ohm internal resistance. Okay, so that's a little bit about how we model a real voltage source. And the most important thing to remember is that the ideal voltage source that we include in that has got a 0 ohm internal resistance in there. And so we add that on externally to account for that, for the real one. Okay? Now, moving on, ideal current source. I can't remember, but I don't think you've come across the current source symbol before. But those two circles interlinked like that is a symbol used for a current source. So we got here a constant current source of 2 amps. So if that was ideal, it would have an infinite internal resistance. What it means is all of that 2 amps is always going to go through the load regardless of what that load resistance is. None of the current is going to get lost anywhere else. Yeah? Always deliver the same current and have its terminal voltage determined by the load resistor. So the voltage here would essentially be determined by what we've got connected there, and it will be the 2 amps times. So if there was 10 ohms, that voltage there would be 20 volts. If I made it 2 ohms, the voltage at the terminals would be 4 volts. Yeah? Okay? You must remember that it is impossible. We can design power supplies that will, between a certain range of currents, hold the voltage stable. So we can say we want to stabilise the voltage at 12 volts regardless of current, and it will do so between a certain range of currents, let's say 0 to 2 amps, a stable 12 volts. What that means is if you go above the 2 amps, you're going to start losing voltage. Okay? Or we can say we want to hold our current stable and let the voltage vary. But you cannot hold 12 volts and 2 amps. Not possible if you vary the load. Okay? It's not possible to hold both quantities as stable. So this ideal current source would always deliver the same current regardless of the load resistance. However, real current sources, like they can't supply an ideal voltage all the time, they can't supply an ideal current either. So the way we represent a real current source is by having its internal resistance as a parallel resistance. So this continues all the time as considered to deliver 2 amps all the time, and it has an internal resistance here of infinite ohms, i.e. an open circuit. So there's nothing lost inside there, but we lose a little bit of current down there. The rest of it goes through the load. So now, depending on how big that load resistor is, if we have a really low load resistor, then most of the current's going to go that way and not too much down there. If that's lower than that, we'll get more current through the load than goes down that resistor. But if this is higher than that, we'll get the most current go down that one because it's the easiest route. Yeah? So a real current source represented by an ideal current source I in parallel with its internal resistance. When the terminals are open circuit, the current I passes through the internal resistance. Okay? It should be noted, it's particularly difficult with this one, that it is a representation of a current source that represents how a real one would behave under load. Okay? I mean, all sources are a source of voltage, but if we're interested in the current, we can consider it. If we want to keep our current constant from our supply, then we represent it as a current source instead. Alright? But the current source is the most difficult one to get students to understand, rather than the voltage source. Quite easy. Okay? But what you must remember about the current source is that ideally it has infinite internal resistance, e.g. open circuit. No current flows through it, it just delivers 2 amps in the case of that one on that page. Okay?
Quick question then.
Yes,
is it not RS then that has the infinite resistance?
No. If we have an ideal car that's got infinite resistance, that's a hard one to get across. But like I just said, no current flows through that. Yeah? But it delivers 2 amps to the circuit. And I know that's a difficult one to get across, but that's how it is. When we put that in, we're representing a real one, because in a real one, as you varied your load, the current delivered to that load would vary. Therefore, we've got to represent that somehow, and we do that by saying it's got a parallel resistance. So we're delivering 2 amps from the ideal source, but some of it is being lost. So we represent that lost current by a parallel path. Our lost voltage comes in a series circuit, doesn't it? Because a series circuit is a voltage divider, a parallel circuit is a current divider. Yeah? Alright?
Could you not just have a switch next to RS on resistor then just completely eliminate it when you've got a low resistor on it to then stop getting a loss down RS?
You're getting hung up with the circuit. It's a representation. It's an extra resistor that will represent the current, the proportion of that 2 amps that's lost within the supply. It's not a real resistor. All you would, if you had that circuit there and that was a current source, 2 amp current source with an internal resistance of 10 ohms, yeah, you wouldn't be able to measure the current in that RS. All you can do is measure this voltage and connect a resistor to those 2 terminals. All of that is internal and it's theoretical. Okay, everything there is inside. If that's a battery that will deliver you 2 amps and it's got an internal resistance of 10 ohms, yeah, that bit is all inside the battery, and you can't get to it to measure the current through there. You can find out what it is, but that resistor doesn't exist. This is a model that will model the behaviour of a battery as a current source.
So confusing means that we're sort of separating the two, like a battery supplies voltage and current is then drawn from that battery.
Yeah.
You're kind of saying that.
But sometimes in circuits, Lewis, it depends on what you're wanting to do. If you want to consider you're going to supply a circuit with a constant current, then you want to consider your supply as a current source. If you're going to supply your circuit with a certain voltage, 10 volts, 20 volts, you'd consider your source as a voltage source. Yeah? And you're going to get the same results through your load, whether you consider it as current or voltage, but it's about what you're interested in. Yeah?
Is that why?
You could even have it mixed.
Is that why, like on data sheets, they always state them? Like, you know, like when you're looking like
Yeah.
power sources.
I mean, if you buy a regulated power supply, and I expect you've got a lot where you work, you can switch them between constant current and constant voltage, can't you? You familiar with that or not? We've got some here where you either switch to hold the current steady and let the voltage drift up and down, or you switch to hold the voltage steady and let the current drift up and down. So you can choose. But you can't have both. It's not possible. And that holding is only within a certain range. Once you go beyond the specification, then the voltage or current will start to drop anyway.
It's like the same
Right?
with pressure and flow, isn't it? You can only have pressure or flow.
Yeah, you
It's
can
hard to
only
maintain
control
both,
pressure
yeah.
or flow. You can't control both at the same time.
Yeah, you do. That's
Because you get a
Every time
varied
you
flow
restrict,
by
yeah.
varying the pressure,
yeah.
and you get a varied pressure by changing the amount of flow you allow, for instance. Okay? I don't want to dwell on that too much longer because I want to move on to using the 2 key facts. Voltage source has got 0 internal resistance, an ideal one. Current source, infinite or open circuit. So what we move on to now is an example, like it. Yeah. Ideal current source of 4 amps has an internal resistance of 60 ohms. Find the load current and the terminal voltage when the load resistance is A 20 ohms and B 150 ohms. So have a go at that for a couple of minutes. Right, I've summarised what you need to do on the board there if you haven't already started that. So I'm calculating my terminal voltage in one go by multiplying the current from the source by the parallel resistance. Plug in those numbers. Has anyone done that? What answer do we get?
60 volts at A.
60 volts there.
And 171.
171 volts there. So this would become, the current is 60 volts over 20 is 3 amps with the 20 ohm load. And the answer to that is 171, so that's 171 over 150 equals
I'm confused.
1.14.
what are you confused with, Carl?
I don't know. I was getting 240 volts because I was doing 4 amps times RS, which is 60, so
Yeah.
240.
But you've got to consider that those two are in parallel. So what I've done here is I've paralleled these two resistors up. That's that bit of the formula to give me the total resistance of those two. And I know that the 4 amps goes through the pair of resistors. Some goes down there, some goes down there, but all of the 4 go through the pair. Remember what this bit does, Carl? That turns that into one resistor, yeah, of equivalent resistance. That all the 4 amps will go through. So that gives me the terminal voltage for 60 volts. What you've done is you've not considered that some of the current's going through there and some going through there.
Yeah, but then shouldn't standard then, that should be delivering 240 volts when nothing's connected to it.
Yes, because that would be the full 4 amps through that 60 ohms. So in theory, if you had a real current source like that, the terminal voltage open circuit would be 120 volts. You're right. Sorry, 240 volts. 4 times 60.
Could you just scroll down a sec, sorry?
Yep. So the second calculation is the same thing, except because we changed the load resistance, we end up with 171 volts at the terminal, 1.14 amps through the load. Yeah. And remember from our work already, when do we get the most power transfer from one to the other?
Matching impedances.
When we match. And that would be true with the current source or the voltage source, is when we match the load to the internal impedance to the source. You're still looking confused, Carl?
No, I'm just working on it.
Not going to fit all this in this week, okay? There are a number of network theorems that electrical engineers can use to analyse networks and determine unknown values. Okay? These include superposition theorem, Thevenin's theorem, Norton's theorem, and maximum power transfer, which you've already come across. Consider how these are used for DC networks first. So we'll keep it fairly simple to start with, and then once we've got reasonably proficient with these, we'll have a go at one, maybe 2 of them on AC circuits as well. Okay. So the first one of those is the theory of superposition. Superposition theorem states that in any network containing more than one source, so this is like where we've got a network where there's 2 batteries, 3 batteries, 4 batteries, the current in, or potential differences across any branch in the network can be found by considering each source separately and adding their effects together. When the contribution of one source, battery 1, has been calculated, for instance, all other sources in the network are replaced by resistance equal to that ideal internal resistance. So if we got 2 batteries, battery 1 and battery 2, and we're considering the effect of battery 1, we take battery 2 out and we replace it with what's the ideal internal resistance of a voltage source?
0.
0. So we take the battery out, we replace it with a line representing a short circuit. Okay? This may sound a little complicated, but as long as you apply a methodical approach and label everything carefully, it is really relatively simple. I'm going to go through step by step and do an example, and then there's some questions in your notes for you to have a go at. Okay? So, let's have a look at this example. What we do here is we've got a circuit here with two batteries in it. 12 volt battery V1, 10 volt battery V2. And what we're going to do is use the superposition theorem to calculate the currents in the circuit above and find, through doing that, find the power dissipated in a 30 ohm resistor. Okay? Now, current arrows should be added according to normal convention. However, in some cases it may not be clear, it might not be obvious which way the current's going. So in this circuit, if we just look at that source, we would assume a current in the direction that I've put I1 there, wouldn't we? We always say that's the positive terminal and current's going to flow out of it. Yeah? And then if we do the same to battery 2, there's the positive terminal, current's going to flow out of it in that direction. Okay? Then, looking at this node, two currents going in, well, the third one, it's natural at this stage to make the assumption that it's coming out and going down that way. Yeah? How will I know if I put, when I've done my analysis, if I put any of them current arrows on the wrong way?
Equals 0.
So if that current is not going in that direction, that's going in that way, what will my result look like for I1? So if this current is actually not going in that direction, is actually going in that direction, what will be my result when I calculate I1? If I follow all the rules. Can you remember? That will come out as negative. So what you mustn't do with these circuit theorems is if you get a negative current, necessarily think that's wrong. What it means is the arrow you put on in the first place, as long as you've followed all the rules correctly, the arrow you put on in the first place was actually a wrong assumption, and that battery's not delivering current, it's taken it in, it's being charged. Yeah? Because what we've got here, what we could consider we got here, is a 12 volt battery with its 6 ohm internal resistance, a 10 volt battery with its 5 ohm internal resistance, and a load resistor. That's what we could consider we got. You see that? Yeah? Alright, Carl? Two batteries with their internal resistances from our previous model. Alright? So that could be a simple battery charger. That 12 volt battery charging that. And if it is, then that current is going to come out negative because it's actually going to be going that way and charging it up. Alright, but let's find out what answer we get when we follow that through. So, they're the current arrows on the original circuit, and we'll come back to that later. Okay? We might change our mind. So, first thing we do, right, is we take out V2 and replace it with a 0 ohm, because we know that an ideal voltage source, which is what that was, has 0 internal resistance. We link it out. Yeah? Then we add current arrows as per normal convention for each part of the circuit. So if we got a voltage with a plus there, we'd say current was flowing I1. We're going to call that I1A. Yeah, for I1 in circuit A. We would say current would flow down there, I3A, and we would say current will flow down there, I2A. Yep. Everyone in agreement so far? So, what currents can I find? How am I going to tackle this problem? Find these three currents. How do I start?
Parallel resistance.
Find parallel resistance. What did you say, Carl?
Resistance.
Yeah, because what will the total resistance give me in this instance?
Total resistance.
Yeah, but then what can I find from that?
Total current.
Total current, and the total current is which current on the?
Y1A.
It's the I1A, yeah? So if I find RT, I'm going to do it all in one go. Are you happy with that?
Go for it.
That's R1. That's in series with those two in parallel. So it's R1 plus R2, R3 over R2 plus R3. It's going to calculate that all in one go. There's 6 plus 30. Go in the order they're in, sorry. As 5 times 30 over 35 equals, buttons pushed please.
.3.
10.3 ohms. Yeah. We can then do, therefore, I1A is equal to can we do that now or not? Yeah.
1.16.
Over RT equals 12 over 10.3 equals, what did you say it was, Lewis?
1.17 amps.
1.17. Three significant figures, yeah? Alright, everybody happy with that? Where do I go now? So I've now found, let's write that on a diagram. 1.17 amps. If I find this current, I can then find that one, can't I? Or if I find that one, I can find the third one.
Yeah.
So how am I going to find one of those other currents? How would you suggest I do it?
Basic Ohm's law, really, isn't it? Because you've got your resistance and your supply voltage.
Yeah, but what if we were to draw voltage arrows on this circuit? We got current coming round here, so we got a VR1 there, haven't we? And we got a V2 there that's across both of them because they're in parallel. Yeah, do you agree with that, Carl? Same voltage across two parallel resistors. Electrically, that point there is the same as that point there. Agree with those, both of those things? Yeah? So how can I get that voltage with what I already know? Because if I find that, I can find the current through this resistor, can't I? What law do you know that will allow you to use the other voltages you know in that circuit? Can I calculate VR1?
Yes.
Yeah?
Work out the volt drop, and then you know the voltage left, and then
So I'm going to do it all in one go, right? Therefore, by Kirchhoff's voltage law, VR1 is equal to what? Oh, sorry, hang on. By Kirchhoff's voltage law, no, I won't do it like that. I'll change my mind. How do I calculate VR1? It is IT times R1. 1.17 times 6 ohms equals. Follow me, Carl? Yeah?
Yep.
So what do that equal?
7.02
Volts. Therefore, VR2, and it might, we've got a voltage loop here. One, remember what we did before? One clockwise arrow, two anti-clockwise arrows. So these two must add up to that one. So we know that one. If we take this VR1 away from that 12 volts, we must have VR2. Kirchhoff's voltage law. So VR2 is equal to V1 minus VR1. 12 minus 7.02 equals 4.98 volts. Therefore, I2 is equal to VR2 over R2, 4.98 divided by, and I'm going to keep, that should be I2A as well, because we're only working with the A circuit at the moment. I2A, 4.98 over, what was that R2 resistance? 5 ohms equals. What we got? Luke.
0.996.
So I2A is 0.996 amps. Yep. And now I3A, that must be I1A, take away that little bit, mustn't it? By Kirchhoff's current law. Yeah? You with us, Carl? Yeah? So the current law equation for here, you've got one going in and two coming out, and I would rearrange that. But this current down here must be that 1.17 take away 0.996. So lastly, I'll do that one in red, so we've got them in three different colours. I3A is equal to I1A minus I2A. That is the 1.17 minus the 0.996 equals 0.174 amps. So here we've got 0.174 amps. Alright? So we've done circuit A, the version with just V1 in it. Yeah. So your job now is to do the same thing with that. Let's just put the current arrows on it first. This is circuit B. So you can keep the numbers the same. Which way would I put a current arrow on this leg coming out of the battery, Carl?
Sorry?
I've replaced V1 now with a short. So V1's been took out and short circuited, replaced with that ideal internal resistance. Which way would I put a current arrow up here?
Person R3 and R1.
Yeah, that way. So that would be I2, B. Yeah. Which way would I put a current arrow through R3?
Down.
Down. I3B. And through R2?
Down.
Down. I1B. Yeah. So, like we did for the circuit A, calculate the three currents I1B, I2B, and I3B. Please. Right guys, I started to write some of it out. So we calculate the total resistance. What do we get? Carl got 10 ohms. Do you all agree with that?
Yeah, I got 10 ohms.
Yeah. So that makes that I2B 10 over 10, 1 amp. Yep. VR2 is I2B times R2. So that's 1 times 5 equals 5 volts. The next bit
V3
It's 5 volts.
equals 10 minus 5 equals 5 volts. Speed this up a little bit. Yeah. That will give us what?
I1B.
I1B, which is
5 over 6.
VR3 over R1, 5 over 6.
Yeah.
833 amps.
0.833 amps. Yeah. And that means
I3B is just
I3B
minus I1B.
equals I2B minus I1B, which is 1 minus 0.833 equals
0.127.
77, is it?
Oh yeah, I got
6, 7.
83.
Yeah,
I
I
just
put
had to pen through.
166.
I'll do. Okay. So, keeping your results in mind, what I've done here is I've added to the original circuit all the currents from circuit A. So we now add them for circuit B. Circuit B, the current here was in that direction, wasn't it? And what was it? What was I1B?
0.833.
0.833. Amps. For circuit B, the current here was in that direction, and what was it? 1 amp, wasn't it?
Yep.
And for circuit B, this current was in that direction, and it was
0.167.
okay. So, what we now have to do is find the sum of the currents in each leg. The easiest way to do that is say, if arrows same direction, add. Oh, I'll put it down there, look. And if they're in opposite directions, subtract, and the resultant is in the direction of the largest one. Yeah? So if we take I3, well, let's take them in order. Therefore, I1 is equal to, so we look at I1, we've got 1.7 amps left to right, 0.833 amps right to left. So therefore, the 0.1, think of it as the 1.17 is the biggest, that's going to push back on the other one. We're going to end up with this being I1A minus I1B, that is 1.17 minus 0.833 equals 0.337 amps. Yeah? I2 is, we've got 1 amp and 0.996, so I2B is bigger than I2A, just a little bit, isn't it? So that's going to be I2B, take away I2A, which is the 1 amp, take away the 0.996 equals 0.004 amps. Yep. And lastly, I3, they're both going in the same direction, so that must be I3A plus I3B, which is 0.167 plus 0.0174 equals what?
Um, 0.338 amps.
Now that looks a little bit dodgy because technically those two should add up to that one, but there's some, we got a tiny little current there as I2, and our rounding has lost 3 milliamps of it. Sorry?
0.341.
What for what? This?
That, yeah.
Yeah.
Which does add up to the other two.
Depends how. It depends what rounding you've done. Yeah. So that particular example, I mean, in some ways maybe I'll modify that example a little bit so it's not quite as close to 0.
167, 174 doesn't make 338.
Does it not? That's what someone told me it was. I shouldn't always listen to everyone.
Yeah, 7 and 4 is 11.
That's 11. 7, 6, 13 is 14. 3, 4, 1. Now they do add up to each other. I just writ down what someone called out to me, which maybe I should have done. Okay. So now now they're right. They do those two top I1 and I2 add up to I3. So overall in this circuit, what we've actually got, I'm going to put them in green. The actual currents, I3 is 0.341. This current here, I2, is in the direction of I2B. So we've actually got 0.004 amps flowing out of there. and this one here is actually 0.337 amps. And to answer the original question, what's the power dissipated in the 30 ohm resistor? There's the 0.341 squared times 30. Push the buttons, please.
Three.
0.48, 3.48. Units?
Power watts.
May appear like a long-winded method, but it's a good method
Because
because it gets you where you want to be. Okay. The other two we're going to look at in detail, Norton's and Thevenin's, are good for a different purpose to this one. Norton's and Thevenin's is where you're interested in the current and voltage and situation for one component in the circuit, the load resistor. This particular method will give you all the currents in the network. Norton's and Thevenin's won't do that. Norton's and Thevenin's will simplify the circuit, and that's useful then because you can use the simplified circuit to see what happens when you change the load. Whereas if you tried to do that with this circuit, you'd be doing all those calculations over and over again. As you'll see, Norton's and Thevenin's make that easier. Okay, so there are some tutorial questions about page 11 and 12 in the notes. Have a go, see how you get on. Alright? And you're really going to have to be having a go at some of these outside the class time, please.
What page did you say, sir?
That's at the end of the section on superposition. I think it's about page 12, Luke.